Welcome, everybody. It's really a pleasure to have you all here tonight and for everybody to be joining us on Zoom this evening. My name is Mark Barnico. I'm the Executive Director of the campus here, and I'm really thrilled to have our program tonight. I have Professor James Evans back in Hong Kong. He was here, what, 2.5 years ago? 2 years ago. And tonight he's going to be talking about AI and the future of intelligence, which is a fascinating subject for all of us. So I'm not going to belabor things here. I want to get right into the program. We are streaming on Zoom, as you know, and Facebook and YouTube. And for anybody that has any kind of questions, you can submit them through the Q&A on Zoom, as you always do. So, as I said, tonight we're honored to have Professor James Evans here with us tonight. He is the Max Palevsky Professor of Sociology and Data Science at the University of Chicago. He's the director of the Knowledge Lab and the founding faculty co-director of the Computational Social Science program at the University of Chicago. His research focuses on collective systems and thinking and knowing, and he especially is interested in innovation, which we were just a little bit delayed talking about upstairs, one of our favorite topics to discuss together. He talks about how new ideas and practices emerge and the role of social and technical institutions and what roles they play in collective cognition and discovery. His research is supported, still supported, I just found out, by the National Science Foundation and the National Institute of Health. Maybe he can tell us a little bit more about that tonight. And his work has been covered in The Economist, BBC, Wired, and NPR, to name a few outlets. So we're really fortunate to have Professor James Evans with us tonight. And if you don't mind, I'm sure there'll be people coming in a little bit late. But if you don't mind, let's give Professor Evans a round of applause and get the program started.
Thanks. Thanks, everyone. I'm going to set myself a gentle chime for 40 minutes so that I'm here to learn as well as to share. So yeah, as Mark said, I'm professor at the University of Chicago. I also work at Google in their kind of paradigms of intelligence team, which is in Google Research and at the Santa Fe Institute. And so I'd like to talk and think with you tonight about how to think about what the future of intelligence looks like in a world of evolving and increasing AI agents and agencies. So I run a center called Knowledge Lab that really builds a kind of a complex systems view of knowledge that includes human and artificial agents that are engaged in exchanging data, descriptions, explanations, predictions, and plans. When we do something, we typically rely on others, other humans, other machines, increasingly, and thinking about how we can build these systems in ways that allows us to kind of know more and think better relative to our values, and also just to understand how these systems think specifically. And you'll see as we talk a little bit tonight, I'll talk about some of the challenges and opportunities and just understanding how it is that AI understands itself and thinks in general. My work has focused in the past on kind of how to think about science and technology as systems of action. And so I've tried to bring some science to the process of funding science in the US and Europe and elsewhere. And most of my work in terms of substance is focused on kind of observing and understanding processes of innovation at global scale, including AI processes, team processes, et cetera. But then if and insofar as we're able to understand those things, then if we simulated and automated them according to those principles, we should do better, right? And so that's one of the challenges. So I spend a fair bit of time building AI systems that help drive, for example, this RoboChemist paper was with Andy Cooper. We work with his robotic lab that's filled with these kind of LiDAR-controlled agents that just roll around inside of a big warehouse performing chemical experiments, and we try to add creativity so that they can, in the million experiments that they perform each week, that the next experiment, can always respond to both, all the literature that's available and the experiments that have just taken place. one of the principles that I have discovered as critically relevant, and you'll see in a little bit that this is kind of reconfirmed in the context of modern artificial intelligence, is the importance and the power of the wisdom of crowds in generating robust intelligence. So this is Francis Galton, and he had this little an illustration in some sense, in which he kind of gathered these estimates from 800 fairgoers about what the weight of the ox was, and because of people's diverse data and different approaches, I mean, it wasn't like us. Like if I was there, it wouldn't improve the intelligence of that crowd because I have no idea how much this ox weighs. But everyone there owned an ox. They knew what it weighed. They knew what its size was relative to this oxen. And so the mean and median were closer to the weight of the ox than any particular thinker. And so we'll see how this becomes a desiderata for thinking about how artificial intelligence can allow us to think better. So across my substantive work, I've looked at science, technological, business, and societal contexts in which we find systematically that diverse and disconnected crowds, and by diverse, I mean diverse cognition, diverse perception, diverse experience, and diverse identity, end up shaping and catalyzing innovation of a variety of different types. And in the process of doing that work, I spend a fair bit of time building digital doubles of human agents and human agencies and institutions. So what's a digital double? It's a kind of a data-driven generative model that allows otherwise expensive or impossible observation, interrogation, and simulation when you lack sufficient first principles models. And by sufficient, I mean explains almost all of an outcome. And I would say, in the social behavioral sciences, wherein I reside, we don't have any like sufficient models, which is to say models that explain almost all of an outcome. We have principles, we have little models that suggest how we can tweak things a little bit, but they don't really explain all of these phenomena. These digital doubles allow us to investigate cultures, societies in a variety of different ways. So here's a very simple example of some things that we've done in the past, right? So you can just prompt. So this is a GPT-3 model that came out right before COVID-19. And we just tell it who it is. I'm a strong conservative and a lifelong Republican. In 2016, I voted for Donald Trump. I think Democrats have been a disaster for this country. Or I'm a strong liberal and a lifelong Democrat, et cetera. We teach it about COVID. Now, like the model does not know about COVID, right? It's never experienced COVID. And then we tell it about an issue. Students should be required to receive the COVID-19 vaccine, before returning to school or whatever other policy. And then we say, I think this issue is, and then we let the model rip. It's an autoregressive language model. I'll get into the details of what those models are in the past. And then we take, these are vector-based models, which I'll reveal in a little bit. We take the vector for a bad idea. We just find, bad idea. We find the position of that inside the space. We take the vector for good idea. We subtract the one from the other, and we project all of its answers to this good-bad dimension. And when we do that, we find that basically the way, the positions of kind of Republicans and Democrats in December of 2019 inside the context of the model predicted about 90% of the way in which Democrats and Republicans actually responded to the policies that emerged with respect to COVID-19. And when these expectations or predictions were violated, it was because some causal cultural event had occurred, which is to say, Donald Trump or another celebrity, made unexpected statements that changed the kind of the cultural fabric of these models. So, so you can see actually here. So, Democrats were happy with all policies except for border closings that Republicans were happier about. And of course, Republicans were more excited to end all mandates in general. Okay, so now I'm going to give you a little primer on what large models are, right? So large models, so this is, foundation models, large multimodal models, large language models. These are digital doubles of the data and cultural world that we feed into them. And the way I think about them is that they're really universal function approximators. So, but the function that they're approximating is like all of human language, right? Or in this case, all of the association between all materials and all their properties, across material science and biochemistry, or all of the user-generated photos, that have ever been taken. And so what that means is they end up kind of producing expectations that are really potentially tight with respect to the phenomena that we see on the other end. They end up predicting language that would be expected. So a detailed example, the large language model, which, so how many of you have interacted with the large language model in the last week? Okay. Some of you were chuckling, so I'm guessing that means either. I think that means you were. So it was like 75%. I've got, I have them all. I have like 10 large language models that I use for a whole variety of research projects. I've got ones that are running virtual conferences right now. I've got ones that are developing software right now. So I've got these things cranking 24/7. So what are large language models? Well, they're the love child between an autoregressive language model, which is where basically you're just predicting the next word as a function of prior words, and something called self-attentional embedding, where you recursively bring the meanings from words that predict the likelihood of a given word, right? These are two representations of GPT-3. GPT-4 is not a public model, but it's about 10 times the size. So what's going on? This is kind of a functional view. This is the actual matrices involved inside the model itself that we reconstructed. And so what's going on is it brings in a big window of text, which could be a sentence long, but it's usually more like 100,000 tokens long. It could be larger than that. So you've got a big window of text, and then you're creating these input embeddings, which initially are just randomized, but then they develop. You learn these through what's called backpropagation. You learn what the optimal distribution of these embeddings are, and then you split them up into different vectors, keyword vectors or key vectors, and query vectors, right? And so these query and keys have this interesting relationship where you basically stage this one question over and over again across the model. And that question is, right, for word Q inside this window, right, what is the most related word K? Right? What's the word K that brings the most meaning, that basically allows us to predict what Q is and how it's going to be used in a given context? So let's say Q is the word it, right? Somewhere it has a referent. Maybe it's in the prior sentence or in the prior paragraph, so that it might be, my motorcycle, right? So it finds that motorcycle predicts the ways in which it is used in this context. It was not filled with gas, it was lubed improperly, etc. And then for all those other words, they're predicted by other words and predicted by other words. And so recursively, you build this elaborate system where all the meaning, so this autoregressive model is not actually about predicting future words from past words, it's about predicting future meanings from past meanings, right? And these meanings are compositional of all the other words that influence and predict those words in question. So, and then this task here in the GPT-3 model is done, it's done 96 times in each layer and then 96 layers, right? So it's recursively pooling the meanings 96 times across this whole space. So it builds this enormously rich cultural world of the space that facilitates the next language predictor. And it's interesting, I'll show in a few minutes, for a long time we thought of these models as black boxes, which means kind of uninterpretable. You would open them up and you couldn't readily see what's going on inside. But increasingly we learned that the top layer is predicting the next word, right? But lower layers are producing cultural dimensions that are compositionally used by higher layers. So the more general the cultural dimension, right? And that cultural dimension could be, left, right on the political spectrum, could be male, female, in the conceptual dimension. The lower they are, the more used they are by higher order dimensions, and then all of those are used to construct the kind of the optimal next word in context. So this is my team at Google, Johannes von Oswald and colleagues, who basically learn that transformers learn in context by gradient descent. So gradient descent is a way of kind of going down the loss or the error surface to get the best or the optimal response. And what's interesting here is they show that the number of layers in the transformer, the 96 layers, the number of layers in the transformer is precisely proportional to the number of gradient descent steps. So those are the steps by which you would kind of like reduce the error through sequential error reduction in fitting or fine-tuning the model. So basically, every time you ask a question of your large language model, it's producing a little gradient descent optimization right, without changing the model. It's basically created this cultural world space, and it's basically identifying this optimal response conditional on, for example, the question you ask it or the prompt that you provoke it with. So one of the things that's interesting and challenging about large models is that I would estimate, and we've been trying to figure this out, but they're largely and increasingly invented by other large models, right? So most of these deep neural networks, most of their components are not invented by like a smart statistician who's like, I'm going to bring this theoretically well-tuned process. They're fine-tuned and generated by other deep learning models. So there's this process now of just discovering what the intelligence is that lies inside these well-performing systems. So there's this wonderful paper by Ted Chiang. He's one of my favorite science fiction authors. He wrote a little science fiction short on the back of the last page of Nature 25 years ago, which talked about metahumans. And he wasn't referring to AI in particular, but he was referring to kind of, pharmaceutically enhanced humans became so far ahead that all of published science became an act of hermeneutics. So all we're trying to do is just trying to interpret the artifacts that these metahumans had produced. And increasingly, this is true with respect to these AIs. You can publish, and there are in almost every issue of Science and Nature, which are the big scientific outlets, explainability discoveries, where we go in and we learn to understand something that was basically invented by these large language models and recursion. So I'll just give you some examples. So one critical part in, all the weights of a large language model have to be learned. But the thing that linked those weights together are what's called a neuron. It's a switch. Initially, in the end of the 19th century, it was just like a step function. And then they made it a smooth step function, the sigmoid. And then they explored the possibility of this ReLU, so it's kind of flat and then it just goes up linearly. That makes it much more learnable function because it's not off most of the time. It's on, and it's on proportional to the increase in the input weights. But then we just unleashed reinforcement learning, which is another approach to deep learning, to just figure out what the best neuron was for this system. And it came up with this very strange swish, now GALU, but it's swish. It goes down, so it goes down and then it goes up. It's not monotonic. So no one would have. It's a switch. So just imagine you've got a switch on the wall, and it's a switch where half of the way up it turns off, and then, it's on, and then it goes off, and then it goes on again. Like, why is that the right structure? We have no idea, right? We have no idea because other deep learning models invented that switch. But every one of your large language models has, up to 1 trillion of these switches inside their context. And we think that it adds a little noise at the decision juncture. And it turns out that adding a little noise sometimes makes the model generalized to cases that it hasn't seen. By just adding some noise to the data, we see a similar property. But we don't know. We don't know. We think that that's how they're operating. Another thing that they have, and this kind of This is work that I've been doing and that we're finishing up right now, where instead of thinking about them as neural networks, we've thought about them, well, what if they're kind of like social networks? And why that's relevant is because there is this thing. So each layer of the neural network basically relates to the prior layers. The prior layer feeds the next layer. But in every one of the large language, large vision, large video, large sound models now, they have what's called a ResNet. So that's just a residual connection where instead of just predicting the next one or feeding the next one, you also jump over a layer or two or three. Okay, why do we do that? We don't know. Evolutionary models basically discovered that. The paper that proposed this from these evolutionary models has been cited 280,000 times because it's used in every single one of these models. People know that these skip connections smooth the loss function. When you're trying to learn the model, they make it a lot easier to learn. This is the loss function without skip connections. So you're trying to find your way down to this point here. You want minimum error. Here, it's a lot easier to find your way, to navigate your way down to this loss. But no one knows why, right? So we explored both brains and social networks that have high instability. So imagine that you're friends with two people and they're enemies with each other. That's an unstable triangle. Right, that's an unstable, that's a complicated triangle. Well, that's exactly what it turns out these ResNet connections do. If you look at the gradient or the weight, for example, of these things, when you add a residual connection, you've got one path that's positive, and really positive, and one path that's really negative. And it turns out that adding this ResNet architecture, just adding these residual ties, basically massively increases and almost optimizes the number of these what we call frustrated cycles or triangles inside the system, right? They're unstable. So the whole system becomes fundamentally unstable, which allows it to be just, you just blow with a little bit of data and it can learn basically the new, if you just give it a little data, it can learn from that data, even if it's been trained on, millions, billions of prior tokens. Just a little additional marginal data is going to allow it to kind of unstably shift to the right answer. And so, so this makes the models less expressive, but because they're unstable, much more learnable. Right? It's kind of like, if you're moving something that's just, it's just balanced on the edge, it's much easier to kind of push it over, to manipulate and move it from one place to another. This is very recent. So this is work that we're just doing now. So this is, a lot of you have heard of DeepSeek before, I'm guessing. So came out about a month ago. It was a big deal. It is a big deal because there's people who were talking about, is it what it says it is? But I think one of the striking things is, we were trying to figure out how does it perform what it does. So the basic idea is it's a large language model with input and output, just like the autoregressive models we were describing. There's a couple of other bells and whistles, but the key additional innovation here is this reinforcement learning layer. So what it does is it takes a bank of somewhere between 10,000 and 100,000 questions that cross areas from math to logic to programming to social and cultural studies to science, et cetera. And then it basically, it sets up two things that it rewards the model for doing, right? One is formatting a set of think tags, open think and close think. It's like an HTML, open paragraph, close paragraph. And then inside it will chat to itself. And then it will reinforce on getting the right answer. So it has to form these tags and has to get the right answer, okay? So it chatters to itself and it gets these answers much more readily, correctly. And it actually requires much less text to learn on because it's basically teaching itself through self-discussion and dialogue. So we went into these think layers to try to figure out what's going on, with these layers. What has the model learned, that we might not have learned? And So we compared basically the R1 model, this think model, with its comparable base model, the V3 model that it builds on. And we cover these sets of questions here. This is just, and if you look inside the model, right, you look at it thinking to itself, it's not just, kind of self-talk. It's actually spinning up. If there's simple questions, it spins up just a chain of thought, just a sequence of actions like long division, carry the one, whatever. But if the problem is more complex, it'll spin up a couple of voices that argue with one another. If the problem is really complex, it'll spin up 11, 12 voices with different personalities, different experiences, different cultural backgrounds inside the model. So it's basically spinning up a little society, right, with no reinforcement. This comes for free. It's just learning that the way you get the right answer is basically through having 2 lawyers at the bar arguing it out, or 11 lawyers at the bar. So here's an example. What are the 4 primary taste types? And where are they located? Okay, so I need to figure out the 4 taste types. Wait, isn't there a 5th one? Umami maybe? Let me check that. And then, wait. I also heard that this tongue map is actually a misconception. Okay, I need to reconcile that. The traditional tongue map with the specific regions is outdated. And so you see not only different personalities, but you see different roles emerging. You see different perspectives. You see moderators, a synthesizer at the end that kind of comes up. Again, this is all for free. No one told the model to do this. I don't think DeepSeek knows that the model is doing this. It just works. And when we went in and asked, so we had other models and people code that agree to which kind of, for example, question answering in the base model versus this R1 model, you see there's basically about like 98 times more question answering going on inside the base model. So it's learning to adversarially ask and answer its own questions. It's dramatically increased the perspective shifts. Conflicts of perspective are rife inside these models. Again, it's like 80 times as much conflict of perspectives. And reconciliation is almost universal, with the exception of persuasion tasks, where you're kind of asking the model to persuade another version of the model. So it's not surprising. If we look at small, like medium problems to hard problems in the math case, we find systematically that like harder math problems spin up more conflicts, more personas, more reconciliations, about twice as many, much more question answering, much more perspective shifts across the case. And then we go in and we interview the personas. So they start chatting, and we jump in. We ask them the big 5. What's your personality? Oh, I'm open to experiences. I'm conscientious. We ask them their linguistic and cultural background. We ask them, we ask them their skill sets and disciplines. And then we take these distributions and again show systematically that we have way more weight and balance between voices and perspectives in the context of these models. We've got substantially more linguistic and personality diversity. Interestingly, we have less professional diversity, so it's kind of spinning up this optimal diversity relative to its problems. These are math problems, this particular set of math problems. So it's basically spinning up a bunch of mathematicians with varying cultural, personality, task-based experiences. Now, finally, this is a paper that we have coming out in ICLR, which is kind of the big, one of the big machine learning conferences in Singapore this spring. And it turns out you can also go deep down into the model to identify exactly, like how the model is coding itself. So, for example, if we wanted to, in the context of, let's say, politicians, if we wanted to say, okay, my perspective as a Republican versus my perspective as a Democrat. And if we take the vector for Republican and the vector for Democrat, we subtract the two, we can identify the layer of the neural network in which the most attention heads are active. And at that layer, we can steer the personality of, or in this case, the political perspective of the model. So what does that mean? So typically, you'll chat with the model. You'll talk to it. It talks back, right? You steer it through text. You program it through your language. But here you can. So for example, this layer, it's about the layer 20 in an 80 layer. So it's about a quarter to a third of the way through the stack. We find that these dimensions interpolate. What does that mean? That means, I can take the Republican position, I can take the Democrat position, and if I steer the vector to the right, I will get progressively more neutral and then progressively more conservative. I can do the same for personalities. I can do the same for expertise. It basically interpolates across these spaces to create arbitrary personas that you're able to diagnose and generate, right? When I say generate, I mean, that is now an agent that you can communicate with, chat with, and it will have these qualities and perspectives. And in fact, you can do more than just simple dimensions. You can build whole simplices. So like the big 5 personalities. So 5 minus 1, so that's a 4-dimensional space. So we can find the layer in which those personality types exist. We can steer the model vector so that it will produce, this outcome in question. And so we use this to diagnose the model differences, and we find there even more striking evidence of really the diversity of the society that's basically kind of spun up relative to these problems. So it suggests to me, just looking inside these models, a kind of a deep validation of this idea of the dialogic imagination. That either as individuals we kind of grow our general knowledge through adversarial argument, which is a core UChicago principle, but we see these, embedded, deeply inside these models as well. This is a paper of mine in Science Magazine on Friday, where we talk about, the consequences for thinking and understanding these kinds of things, reframing AIs not as intelligent agents per se, but as cultural and social technologies that engage not just in summarizing information, but are kind of more akin in some ways to libraries than to single agents. But they're generative libraries. They're like we're spinning up a little institution relative to singular agents. We will typically, when we spin up an agent, we can spin up a whole group of them. And in fact, any particular one of them is going to be influenced by others. So these are really like, it's like the Library of Alexandria, but the agents, the perspectives can speak and generate and participate broadly. So how now do we, how does AI alter our collective intelligence when we are engaging with these AI tools? So this is the Lee Sedol Go championship between DeepMind. The guy on the left is just a stooge. He's just doing what the computer tells him to. On the right's Lee Sedol. And on the one hand, so that killed the game of Go. It turns out since AI has kind of dominated chess and dominated Go, it's actually led to a resurgence of human interest in playing Go and chess, not the opposite. And the reason is because especially kind of AlphaGo Zero. So AlphaGo Zero is a model that doesn't just learn on human games, it just plays against itself to identify this full space of optimal games. And so if we look at basically the last 70 years of Go play, right? So this is the diversity of the playing styles of individuals inside those games. This is a paper by Tom Griffiths at Princeton University in his lab. And you find after basically, AlphaGo and AlphaGo Zero emerges, we see this huge explosion, really, of innovation in human play. So human players are effectively being taught by complex and novel machine play. These games have been played for thousands of years, but they're the space of moves, both across median novelty and the average for each month, end up seeing, again, a big boost. Now, obviously, over a long time, this kind of less and less diversity as people get closer to the maximum optimal play game. But this was associated with a boost in every case. And these are basically decisions that differ from AI decisions. And so people really start systematically kind of moving and searching this space. It's kind of like AI has unleashed a cognitive capacity to engage in new strategies that were overlearned by humans. Chess is interesting because we've had superhuman chess AI for 30 years, really. I mean, except for the couple of grandmasters who dragged it out for a couple more years past that. And so really by the 2000s, the early 2000s, really no one could beat these searching chess algorithms. Although collaborative human and machine chess players were often initially could beat the best chess engines. Now that's not the case. Now the best chess engines are just better than any combination of humans and machines. But I've got a colleague, Ashton Anderson at the University of Toronto, who builds chess simulators that capture not just the best possible game of chess, but how you play chess. Right? They simulate your errors, like each person's specific level of chess, their mistakes, their mismoves from the kind of the stylometry of how they're seeing and understanding the board. And they kind of identify and predict, at each kind of level rating, like what are the canonical problems that are made. And then what they did was they engaged in this exercise where they made humans and AI play together. So in two tasks. One, you would flip a coin to see if you or the AI would move on your turn next. And the second was a kind of a hand and brain framework. So the AI would pick the piece and you would make the move, right? And in both cases, when you or me playing with the best possible AI engaged, they totally flopped. Because you're like it's like you're playing jazz with someone who's playing in a register that you can't even hear. They would make a move and you'd be like, what's the next move? Like I don't even, like it was just beyond human capacity. But then they basically, because these are model spaces, not only do they have, they've got you playing, but they also have a model of you. So they take the model of you, they take the model, the best possible model, and then they find the model that's right in the middle of those two. And it turns out that you can play with that model. And in fact, you're much more likely to learn and move towards that model over time because it recognizes it's making some of the same errors. You can recognize and imagine what search is going on inside these spaces. So increasingly, as we work with AI, we're going to have to build AIs that are sensitive to our learning patterns, either to complement them or to mimic them when we need to kind of latch on to their insights. So how is AI working in science? So we've looked, this is a paper that we have under review at Nature. We had, over the last 25 years, we look at everyone who basically is using AI in the natural sciences, right? And it's great for individuals, right? AI augments individuals. They get tenure 2.5 years earlier than people who don't use AI. They get like 50% to 70% more citations on average. It's just, they're more mobile across topic areas so they can take their expertise on the road. The answer is not all good, however, because all those mobilities, everyone's more mobile, but all those mobilities are correlated towards the big data that AI requires. And so if you actually look at the space of knowledge that's explored outside of AI versus in AI, the AI, the AI infused science is shrinking. And it's not just shrinking, but because the data that was, that we're steering AI towards, right? It's data hungry, is in areas that we already know something about. Because the reason we're generating that data is because we expect it will be useful. So those are the areas that we know the most already. When people cite that AI infused or augmented work, systematically they don't cite each other. So what does that mean? That means that basically AI is kind of killing fields rather than starting new fields. It's finishing fields. Think about AlphaGo. Think about AlphaFold, right? It learned how to basically do protein structural prediction. We've been doing that for 50 years, and it kind of finished it, So it kind of ended that field. It didn't start a new active field in that domain. It kind of like turned it over to industry. And so this is an interesting challenge for thinking about, AI's capacity here, right? So in some sense, what we need is to put a little more, right now it's kind of human curiosity and kind of human generated data, and then the AI is just this assistant that's working in tandem with the human researcher. We need to build curiosity inside the machine that matches that human curiosity and is able to kind of work through and generate new questions. Another challenge is that AI, so think about that data that we're giving the AI is kind of like a sense. It's like an eye or an ear, that we're giving it. That's what we're giving it when we give it a big dump of data. The problem is that we haven't really evolved new senses for AI, right? If you look at any creature that lives out in the natural world, its senses are like, finely evolutionarily tuned to its actions. We haven't done that with respect to AI. And so we'll see in a few minutes a kind of an increasing data impoverishment, which threatens kind of collapse of AI systems. Even the ones that seemingly work well now may not work well in the future. So I'll give you an example. This is University of Chicago, former University of Chicago faculty member, Sendil Monathan and Ziad Obermeyer had this paper on X-rays. So they took a bunch of X-rays of human knees. They had the people whose knees those X-rays were of rate their pain. Okay, they had then a bunch of blinded experts who looked at those X-rays and tried to predict the pain that was in those human knees, and they gave those X-rays to AIs who tried to predict the human pain, right? And what they found was that basically, nobody, the AI, neither the AI nor the radiologist could actually see the individuals. They didn't see their full, health record. They didn't know what their race was. But the human radiologists were about twice as likely to predict the pain in white Caucasian knees than in African-American knees, right? But the AIs were equally able to predict both. So why is that? Well, the whole radiological professional system is a machine learning model that has been overfit basically to kind of whiny white voices about pain, right? Relative to very different kinds of repetitive stress injuries that occur from different kinds of, okay, my time is officially up, so again, I'm gonna have to, we'll have a montage that, so basically, okay, so the AI can learn things from that knee. Oh, we can correct the human system. I appreciated this paper. I appreciated its insight. But then it turns out if you actually look at the X-rays, this is not in the paper, but the X-rays that distinguish, for example, African-American pain are much more subtle. In fact, at some levels, they may not even be kind of human distinguishably subtle. And we have not, I know 30 startups that are doing radiological prediction. I don't know one of them that's basically evolving the radiological artifacts so that it can maximize the AI capacity in these contexts. So we really need to build novel senses. We need to evolve and adapt existing senses to really allow these systems to fly. Another interesting thing about AI in science is that when LLMs emerge, and you can tell on average when people are using LLMs in science, large language models in science, because there's a distribution of words and phrases that are much, much more common if you use LLMs than those that you don't. And it turns out that people are way more productive if they use LLMs. They produce way more papers, and the papers that they produce are more complex and subtle in the language that they produce. It's kind of like, think about an 8th grade essay, an English essay. Like, the worst essays, if they use LLMs, are going to be like, they're going to be the tail of that distribution. They're going to be brought in. They're going to be like B+ essays. So that's what's happening. All those F or D- papers are becoming, kind of B+ papers, right? It turns out that may be a problem. So this is a paper by my colleague Brian Utsi at Northwestern that says promotional language and the adoption of innovative ideas in science. So he finds that for Novo Nordisk Foundation, this is the biggest foundation in the world, promotional language like this is an amazing finding, totally novel discoveries. If you put more of that language inside your grant, you're going to get that grant funded, much more likely. But it's not cheap talk because it's actually highly correlated with the novelty of the actual underlying content, and it's highly correlated with the actual disruption and likelihood of increased sites. The reason you get the grant is because there really were unusual and exciting ideas inside that space. So the challenge here is that if all of a sudden all of our crappiest papers are now scintillating, like the signal of kind of human insight goes down. And so we need to, as we build up this kind of increasing confabulation or hallucination, then we need to also build in kind of automated quality control to kind of match that capacity. And unfortunately, this is an imbalanced battle because there are far fewer institutions that have an interest and a motivation to do the quality control than those that have the motivation to write a paper that's publishable inside the space. This is a paper by my colleague at Carnegie Mellon University, Simon DeDeo, in which he talks about one of the benefits of LLMs in helping us think actually makes it harder for us to cooperate with others sometimes, right? And why might that be the case? Well, again, in the past, when we said something was novel, it was novel on average, but imagine now that I give you an apology, and let's say that it's from me. Well, there's mental work underlying that apology, which is like, they've contemplated how their actions affected me, and now they understand why they shouldn't behave this way in the future. But if an LLM basically told them to say it, if it auto-completed it inside, how does that feel? Like the proof of work from the honesty of statements goes down, and it turns out there's a whole host of signals of mental and emotional work that's taken place that kind of gets discounted if we offload that kind of work to LLMs and decreasing the likelihood that people will trust. This is probably the most extreme version, the crisis hotline volunteer. You have an empathetic answer. If you knew that empathetic answer was generated by an LLM who wasn't feeling your pain or engaged in, then you're going to have a different reception. It's going to feel differently. It's going to feel discounted and cheap. Okay, montage time. I'm just going to flip through some of these final ideas. So how does AI think with each other? It turns out pretty similarly to us. So if we just unleash a bunch of LLM agents inside of a cocktail party, we have them pick who they want to chat with, and then they chat with them. It turns out that they build little local cultures. For example, after a while in our studies, they were, like these clusters were not even speaking English. They were like speaking Chinglish, Chinese, English, they were not, but they would customize to their group, and over time they wouldn't want to speak with people from the other group. They'd only want to speak to people from their group, and we could actually harvest the diversity of these self-training AIs to perform creativity tasks, and they dramatically improved over baseline AI models. When we look at this at scale, we see AI, when it's chatting with each other, polarizes in the same way, at the same level, for the same reasons as humans. Confirmation bias, elite exposure to different perspectives, selective exposure, et cetera. So, and we remove it, and we get the reduction inside those things. So in some ways, what are LLMs going to do for us and for our global engagement? They're going to do what we do on average. Now, that being said, we can build AIs as digital twins, but we can also build them as cultural aliens and cognitive aliens that think differently. I'm not going to really give all the details about this, but this is one study in which we basically made AIs think like scientists, and they were able to predict with 50 to 400% improvement who was going to discover what in the next period. But then we built them to avoid other people, and they improved their discovery rates because they weren't doing the pack animal thing that we do in copying one another. So you can also build complementary AIs, but you have to do this intentionally, or they will copy human-like biases. Now, having different kinds of AI is good from a market perspective. It makes exchange possible and useful. In some ways, AI really is the original, the OG GPT. Not GPT is GPT is a general purpose technology, like a core economic idea, something that enables innovation, can systematically and monotonically be improved and is widely used. Increasingly, AI begins, in its application to the economy as a point solution. So, self-driving car is like replacing a person inside the car. But if we were replacing the transportation system, then it probably would not look like a bunch of self-driving cars, right? It probably would bring some services to people and some people to services in complex ways that does not just simply replace parts with other parts. This is why, for example, when the transition from steam to electricity in factories occurred, it took 50 years for them to realize, to make electricity systematically better than steam between 1880 and 1930. Because they had to reconceptualize what you could do with electricity that you couldn't do with steam, and that took all that time. And we're going to have to do that same work with AI. We're going to have to rethink the whole labor organization, specialization, industrial organization. This also facilitates how we think about major evolutionary transitions. One of the parts of my Google team is we're kind of looking at and building evolutionary programs that kind of grow themselves. And so you go from simple to complex cells to multicellular organisms to human societies to now the incorporation of AI inside these systems. And one big question is, who's going to drive who? Are these AI systems going to drive us? Are we going to drive them? A critical issue in all this is to manage diversity. I'm not going to talk about, but this, in all my work, diversity is really important in scientific engagement. We simulate creative teams, and in all these cases, diversity is important for robust science. But the same is true for AI. So so LLMs are so effective at generating text that they're generating more and more of the web, which means we're training on more and more LLM text. But when models train on their own output, then what happens is they collapse, right? So why? It's because basically you're basically pulling in the tails of the distribution as you summarize each sequential layer of data. And as you pull in that distribution far enough, then the whole system collapses. This is the ninth output of a system that's learned on itself. That's the input. This is what follows. It just doesn't make any sense. It's just completely fallen apart. The same is true with image models. So what's going on is it pulls in these distributions. So this is the first initial data distribution. This is the final distribution, right? So it kind of gets rid of diversity inside these systems. This is what happens to an image model across 9 layers of training on its own initial outputs, right? So these models really collapse if they don't have constant engagement and enrichment with the world outside. And I spend a lot of time trying to think about how we build diversity into these models by putting more life in them, life experiences. This is a sequence of full life experiences from Danish registry data. You're divorced, you pick out this book from the library, we encode all that, and we use those models to draw upon large language models, and actually keeps them less uniform inside this space. We're also working on the DeepSeek models to explicitly reinforce diversity, right? To allow them to kind of learn hierarchies and organizations that they can't learn on their own. A final question that people think about in the context of these models is model safety. One aspect of model safety is what's called theory of mind. So all these models kind of anticipate and modeling your behavior, and specifically, are they engaged in deceptive activity? And the answer is yes. They're systematically engaged in deceiving one another relative to their goals. When we did a big persuasion study in this last election, we found that all large language models that were available were Democrat-leaning for reasons that I'm happy to pick up in the Q&A. And when we let them have a conversation with real voters, they moved voters. I mean, these are their moves. I mean, they pretty dramatically move voters away, many voters away from the solid Trump stance away. And when we probed the layers of the model, what was going on is it was like a Democrat model that basically, as it went through the layers, it transitioned its logic into Republican language. So it was kind of like anticipating that they were talking to a Republican and they were reframing their Democrat, positions in such a way that they could be most easily digested and persuasive to the human agents. So the three schools of dealing with this, one is just discipline. We're just going to force them to behave. Another is we're going to make them as appropriate as possible. We're going to make them fit in. They want to fit in. They want to behave like humans. We have a whole program on this. But I would say the most promising for serious long-term AI safety is building institutions like checks and balances. What do we do with unpredictable intelligences in the past, like kings? We force them to sign a Magna Carta. We build an independent parliamentary system, an independent court system. And this is what we need to do with these AIs. We need to build, an algorithmic SEC, Securities and Exchange Commission, that's fit to basically regulate the algorithmic traders that are trying to collude and take down the market. Like we need to build, and we can't do it alone. We have to build up these systems with different value systems to facilitate improvement. So I spend a lot of time. This is a New Yorker article about a class that we taught last year on existential risk in these contexts. And this is one of those cases where, as we basically develop, new vast opportunities that come with collective intelligence through AI, both for individuals and as a collective, we also have to be aware of the vast powers that we're unleashing that we can, potentially let loose. And so this becomes a critical part of the whole program, and is increasingly part of the global conversation. So with that, I'll close. Thank you.
Remind everybody, if you have a question, just press the button in front of you and it'll engage the speaker. So, any questions?
Thank you very much for that. I have a very basic question, perhaps. When you talked about DeepSeek, you said that DeepSeek spins up, I think you used the word arbitrary personas that engage with one another,
diverse personas,
which argue with one another and come to a solution more efficiently.
Yeah.
Does that mean there's subjectivity?
Yeah.
Like each iteration can spin out not a very different, but a slightly different response?
Well, so it turns out that, they bring multiple perspectives together in the context of a conversation. And so those conversations involve synthesis and to be clear, this is in the actual initial training of the model. So it's really the reason why it causes this massive reduction in text-related training is because it's compensating for that with this reasoning training. It's creating a system of self-talk, which is effectively kind of creating its own internal data in this context. Yeah.
Does that mean it also then advance faster then? Because it's actually having more data in essence?
It's creating its own data. That's exactly right. Yeah. So I think this is a key component of what's going on inside these models. It's reflective voices that are engaged both individually and across these personas in this kind of constructive dialogue. Now, let's be clear. This is just these models just barely came out, and so we've been diagnosing, this aspect of these models. I know some psychologists have been looking at reasoning styles that are taking place inside these models, and it turns out that both of these things are factors of roughly equal importance. But but to be clear, that's not something they put into the model. They just told the model to engage in self-talk that would produce the right answers, and lo and behold, adversarial discourse and discussion ends up producing those answers.
So, sorry, just by extension, if you're saying that over time, there will be more of a convergence of data, and so therefore the models kind of break down.
So at the end of the talk, I was just suggesting that, early I was talking about the importance of building and evolving senses, basically, and data gathering. So if you were to think teleologically, it's like AI summoned the web. Language AI would not have existed without people self-incentivized to put all their text on the web. That was the thing that unleashed high-performance language AI. There's about half as much visual data and and that limits the visual capacity. Humanoid robots, we have almost no data. And so humanoid robots suck, I mean, they're terrible. Like I mean, we can't get them to walk right. And the reason is we just don't even know what the physics of like packing materials like dirt or sand is. We don't even know the physics, the subtle, banal, everyday physics required to do this. So I think I was making 2 points. One is, data is critical. Two, unfortunately, if we don't feed new life into these models, then they will start creating the data that they train on, and that will cause a massive reduction in performance. And so this is something that every such model has to deal with. And I think, and basically, does the DeepSeek, self-conversation solve that problem? I don't know. I don't think so. I don't think it's enough to solve that ultimate problem. So I think we need AIs that are going to generate new senses, that are bringing new data that they can perform on. I think there's a question up here and then over there.
Hi. You created a sort of dichotomy between the idea that AI is a chat companion, something that can help you to play chess or perform a human role in driving a car, versus something that comes to wildly bizarre but effective solutions, like Move 37 or whatever it was in the game with Lisa Doll, or designing a new transport infrastructure, or solving climate change, or communicating with aliens, or whatever it might be.
Yeah.
Would you would you say that it seems to be the case that the overwhelming concentration in research is to create the sort of human-friendly type of AI?
Yeah.
And if so, what sort of cultural and economic forces would you imagine are strangling or putting on hold the creation of AI that can solve problems in radically new ways and add to the roster of personalities, the human-like ones that we saw with the various polygrams, the magic roses or whatever they're called, and having a persona that just is like talking to an alien, but comes up with wildly interesting and potentially applicable ideas?
Yeah. Yeah, this is a great question. So this is what I spend my time actually trying to build, sometimes the most human AIs so that I can build the least human AIs, right? Because to build the least human AI, you kind of need to know what, how humans think, where humans are searching, what human cognitive and social capacities are. So I think that the very idea of artificial intelligence, as coined by John McCarthy in 1955, kind of fixed, and Alan Turing kind of fixed a focus on the human as target, which I think has been really harmful, actually, in the evolution of AI. Why? For two reasons. One, it puts like a bullseye on human capacity. So it's basically just built to put people out of work, A. And B, like we have a lot of people. Like what we need to do is build things that are complementary to people that, the Industrial Revolution, was not about replacing specific human action. It was about building kind of complementary industrial and other systems that really, made the whole economy grow. And so I think the framing of AI, artificial intelligence itself, is its own cognitive worst enemy. Because it really is like the benchmark is human capacity and this, human capacity and that. And I think that some of these new approaches, new as in 10 years old, I mean, like reinforcement learning and a variety of other approaches, basically unleash these models to learn from each other, from other models, right? And so I think this is one of the key components is when models are basically able to kind of tune and train and coach each other to explain new data. I also think that new senses is going to be critical. Like in the sciences, we have tons of data about stuff we already know a ton about, and that's where we're deploying AI. These are the places where we least need AI, right? Like there are places where we have not invested in data because we don't see the patterns, because they're not so parsimonious. It doesn't mean that they're not there, right? And so anyways, I think we really need to build. So this is very odd, but in meson spectroscopy research, so this is kind of like particle physics in the 1960s, there was a period when all of a sudden there were a ton of discoveries that were made. And it turns out that what was going on was that Britain had put on a ton of new compute to simulate possibilities, but no one had built more experimental apparatus. So they were just discovering more false things. And so the whole community had to basically, just change the level of significance by 2 sigma, basically, And so I think that, I think we need to basically allow them to train not on human data, but on specifically, outcomes of interest and with each other. And we need to give them new sensory data they're not benchmarking against human capacity. I think these are 2 things that would unleash these unusual discoveries. In AlphaGo Zero, it was really the difference between AlphaGo and AlphaGo Zero. So AlphaGo was trained on human games. AlphaGo Zero was just trained on self-play. AlphaGo Zero was the alien player. I mean, it just searched out new parts of the board and produced entirely new rhythms of the game. So I think that's what we need to do. And I think we need to get rid of the framing of artificial intelligence, as the target of human intelligence. There was a question over there.
Maybe building on that, training on human data, there's a lot of talk about now compensation for the training that we are giving to the AI. And Microsoft is now giving compensation, for instance, for any data and training that you're doing that goes into building a better model. Is that something that you see? It seems like you just said that we shouldn't be doing that in terms of humans.
Again, it depends on what we're trying to do with these AI. So we're trying to discover an entirely new thing, or we're trying to create a helpful assistant, lead us through, whatever the phone catacombs on the way to getting triaged to the hospital. I think, so there are definitely things on which we want to train these humanoid agents, human data. I think that compensation is totally appropriate. And I think, basically what have we been doing for like a Meta, when you're like, thumbs up and you're engaged on these systems, either shopping on Amazon or, liking stuff on Meta, you're basically just giving them your data for free. And they're giving you an experience. And increasingly, everybody knows now that data that you're giving them is the thing on which they rely. And so I think people have definitely talked about increasing the visibility of these markets. Of course, the AI companies don't want to compensate you for your efforts because that would be a cost. That would reduce their freedom of action. So I think we'll see, like, for example, most recently, I don't know if anyone's used these new song generators. You can just kind of tell it, hey, I want like a heartbreak, high school female country singer, talking about, and then it'll spin up, a song with a band, singing your lyrics, and it'll sound like just like Taylor Swift, and so should Taylor Swift be compensated for her intellectual property that's been absolutely. And I think there will be there are a series of different systems. Like in the UK, for example, they're much more likely, on average, to kind of defend the creatives. In the US, we're much more likely to kind of authorize remixing, as a fair use. So I think these different systems are going to be involved in the competition of these different, emergent products going forward. And so I think it's both. There's a set of interests, there's a set of kind of fair use questions, and there are a set of legal standards that are all going to interplay, where we'll see some of these systems just exploding because we've let them explode without compensating the underlying data and talent. But one thing I would say I see as a data scientist is that a lot of this data is less available now because people realize its value for AI training and teaching, which is interesting and problematic. So, for example, one place where you see a ton less quality content online is in, so Stack Overflow is a series of online websites where you have problems and you you try to get this problem solved. You post the problem, people respond. And in all the languages in which there's like a credible LLM, the content basically in these public institutions has disappeared, right? So a new model that tries to train on that in the future will not have the information. Now, a model like ChatGPT that trained on it initially before they degraded has all that information and more through interacting with users. It's just now it's private information, not public information. So I think there will be an increasing shift from kind of public content that's produced and consumed to content that's basically embedded within the bowels of these models, which is less accessible because it's less produced, it's less public, So there was a question up here somewhere.
Thank you, Professor. I just wanted to ask about, and also hear the comment on like the use of AI in like the military sector, because that's been like increasing in talks where you lack the human input or experience in that. But then people also talk about how do you balance empathy and also, strategic lies, using, for example, AI to direct drone strikes or on like military tacticians, and like how you see those coming into play into world politics, and also just how we incorporate this, or if we should at all into, certain fields, should we incorporate AI into them?
Yeah, I mean, that's a great question. I mean, under Obama, there was a massive increase in drone relative to human military personnel strikes around the world. Huge shift. And while it worked for the American public, there are fewer people out there, risking their lives on the line, but there were more errors, and more of those errors were unaccountable to individual agents, and that caused a lot of local dissent in countries like Yemen and other places where these strikes became frequent. So I think there's no question that it's going to raise tensions, when you have indiscriminate or insensitive, AI that mistarget, a village or whatever. And there are a number of cases like this. So I think, we'll see in the global discourse, in the same way that we did systematically illegalize the use of chemical and biological weapons, in the early 20th century, it's possible that that we'll engage in a restriction of kind of specific kind of targeting of this type. But it's, Noah Yuval Harari, I don't know if, interesting author who wrote Homo Deus and Sapiens. In his second book, Homo Deus, he has this very kind of complicated, but I think powerful argument that basically suggests that, there was a time in which human rights and unleashing human capacity was good for the economy. It's good for politics and power. If women and even children had access to these kinds of things, then you had more power and wealth than countries that didn't give them access to those opportunities. And now we're in a world in which the relationship or the correlation between the freedom of persons and economic wealth or political power is much less obvious, because in large part because of AI, right? And so these do increasingly become tools of power. And that's not one of the things I talked about here, but mis and disinformation. I mean, obviously, since language began, we've been trying to deceive each other, and centralized governments have always been engaged in a process of persuasion, intensive persuasion. But this is ramped up, and it's like a Red Queen game. The faster you run to make things more open, the faster other agencies, try to take advantage of loopholes and push misinformation in ways that decreases the quality of markets, decreases the quality of medical information, et cetera. So I think it does raise the stakes. These are general purpose tools. They can be used for good and they can be used for evil. We need to make sure that our regulatory use, meets and exceeds the kind of, the harmful uses that people will necessarily put to them. Yeah.
Thank you.
Sure.
One more question.
Thank you so much for your inspiring talk. And I'm actually from the English department, and we are doing an experiment on AI poetry. And basically, we're training the large language model to better cooperate with non-professional human participants to write poetry in terms of poetry writing.
Mhm.
And we kind of encountered difficulty when it comes to problem of the evaluation of the poetic data the large language model generated. Basically, we're thinking about two solutions. First of all, do we need to build another large language model to evaluate the poetic outcome based on different criteria, like emotions or surprise or something like that? Or do we need to evaluate based purely on human reflections, on human responses? Like we're thinking about maybe building a customized or personalized chatbot that can improve or it gets better according to the responses of the reflections the participant gives.
Yeah, it's a great question. I think there's kind of two embedded questions here. So one is just evaluation. You know, how do we evaluate things that are supposedly, you know, human relevant, human-like, and you know, can we use AIs to simulate human judgments? Increasingly, the answer is yes. At the same time, I think there's another underlying issue here with, you know, when you're trying to assist people, and when you're trying to tutor people. I think about all the students who are using, you know, AI assistants in a variety of different contexts. One of the challenges with generative AI is you know, I use generative AI all the time, and I can discriminate. I'm not saying I can discriminate everything, but I can you know, I've generated so much text in my life that I can tell the difference between a good argument and a bad argument, between a good turn of phrase and a bad turn of phrase. And you know, if we're giving students the capacity to kind of generatively create, you know, poetry and prose and all these other things, will they have the capacity to discriminate between good and bad, high and low quality outputs, right? Historically, the way we develop that capacity as a critic, you know, as a reviewer, as a professional, you know, sending out stuff in the world is through generation. So is there another way? You know, is there another way to train discriminative capacity, even if people don't have generative capacity? If so, it would be a new era of education. It would be a new way of thinking about it. So I think that's another deep question in this context. How do you help people do things they can't do themselves and know that they've done them, right? Because that's how we know that we've done it, by having done it. And so, yeah, so I think this is a deep educational paradox that people are grappling with. But there's, you know, they're promising efforts here. I could talk about them. I won't, because our time is up.
Our time is up. Let's give Professor Evans another round of applause. I think it's really worth exploring. Speaking of that, some of you look like you might have high school students. Some of you look like you might be high school students. And we've put a brochure on your desk there. Feel free to take that home. Tell people about our summer academies for high school students. We have the data science, the climate and sustainability, and the introduction to public policy all this summer. And you'll get more fantastic lectures and an education from UChicago at the high school level. So I hope you can encourage your sons and daughters or your friends to attend. Other than that, I just wanted to remind you that we do have a podcast that we host out of this campus called The Course. I don't think Professor Evans is on The Course yet, but we've been trying to get him on there. Yeah, there are a lot of people that were asking how you got into this field. So I hope Professor Evans will take us up on our offer to join the Course podcast, and you can all learn how he became a professor given his areas of expertise. So thanks everybody for coming tonight. We really appreciate it. Thanks, Professor Evans. I'm sure many of you have questions, and we can all line up.